This video will be an introduction to the basic concepts of cyclic voltammetry. Cyclic voltammetry is a commonly used electrochemical technique, which in our case will be used to determine the concentration of acetaminophen in a children's pain relief elixir. All right, so what we have to understand here first is that we're going to be using an instrument called a potentiostat. The potentiostat will be connected to the electrochemical cell, which we will be constructing here in a few moments. And the job of the potentiostat is to apply an appropriate potential or voltage to the electrode where the oxidation and reduction of the analyte of interest will take place. Now, as a result of that oxidation reduction process, a current will also flow at that electrode, which becomes our analytical signal. So the potentiostat's other job is to measure that current flowing at that electrode where the oxidation and reduction of the analyte takes place. All right, so the first thing we would do is we would come in and we would turn on the potentiostat, which I've already done here. The next thing that we would do is we would make sure that the potentiostat is in the external mode, and that means now that the potentiostat will be awaiting instructions from the computer software that will then be controlling it and allowing for us to measure the current. So we come over to the computer at this point to bring up the software. The software is accessed through our shortcut to Aftermath here, which we can double click on, which brings up our menu. Now there's no username or password required here, so we're going to just say OK. And that brings us into the main menu of the software. So here, to perform an experiment, we'll see that we have a list of various experiments that we can access here. Cyclic voltammetry is the one that we want to look at today, so we're going to double click there. Now, to set up the experiment, we have to actually set up the potential waveform that we're going to be applying to the electrode of interest. So this is what our basic menu here will allow us to do. So we're going to be placing some numbers into these fields here. So to begin with, we want to utilize 3 segments, and I'll explain that here momentarily. We need to have an initial potential. So that's the voltage where we're going to start the experiment. And I'm going to set that at 0 volts. I'm going to set our upper potential or positive most potential at 0.8 volts. This is somewhat arbitrary, but I generally want to make sure that I'm getting out to a positive enough voltage that I can actually ensure oxidation of the acetaminophen. The lower potential, which will be our second segment, will take us down to, let's say, minus 0.3 volts. I think that's what I want to put in. All right, and then our final potential is going to be 0 volts. I want to initiate in a rising direction, meaning that my first segment will be at 0 volts and I'm going to scan out to 0.8 volts. So I'm increasing my voltage. So I'm moving in the positive direction initially. I'm going to keep the sweep rate, which is the rate at which the voltage changes during each segment, at 100 millivolts per second. And now for the current range, I prefer to actually manually go in and change that. So I can go to auto and I can now change that to whatever range I want. So I'm going to start with 5 microamps as a guess. And again, I can come back and change that as need be. All right, so at this point, we're ready to run the experiment, except that we need to set up the cell. So when the time comes, we'll come back and hit perform. Now at this point, I'm going to come back around to the electrochemical cell itself. Now the cell, of course, is going to be in a container. And the container right now holds the 1 molar buffered saline solution. So we're going to run a cyclic voltammogram on that to determine what the background voltammetry is going to look like. Now to do this, I have to set up the 3 electrodes in my 3 electrode cell. The silver colored electrode that you see at the top is actually a platinum rod, and that will be our counter or auxiliary electrode. We'll also need a reference electrode. That's the one that you see right here. It sort of looks like glass, and that's a silver chloride reference electrode. And then finally the working electrode is the one at the bottom here, and that, as I'm going to show you momentarily, is going to be a carbon disc electrode. All right, so A few things that we have to do to set up first. So I'm going to set up my tripod so that I can get both hands free here. So I'm going to focus down on this region right here. And what we need to do initially is we need to actually clean the working electrode. So you see here the working electrode. Now you might be able to see it here, but there's a glassy carbon disc on the end. I think you can see it right there. Now what happens is that organic matter will absorb to that carbon disc. So what that means is that the electrode will be fouled. So we need to clean the electrode now so that efficient electron transfer can take place there. So essentially I have some sandpaper here that I've wetted down, and I'm just going to grind the electrode along that sandpaper there to abrade off any material that may be absorbed to the electrode surface. Okay, once that's done, I can come back with a Kim wipe and I can wipe down the surface of the electrode and take a look at it. And it should be mirror polished at this point. You probably can't see it, but it has sort of a mirror polished finish to it. Okay, so I know now that the electrode is clean. Now the next thing that I want to do is I want to set up the electrochemical cell. So I'm going to now focus on the cell itself, and I'm going to put the electrodes together into this little cell holder here. Okay, so what we can do is come back around, place the working electrode in there along with the auxiliary electrode. We'll also pick up the reference electrode and place that in there as well. And what I end up with is an assembly that looks something like this. Okay, that whole assembly will be dipped into the cell container. And as I mentioned before, the cell container is filled to about 2/3 or halfway point with the buffer solution here. Okay, so now you can come in here and see that. All right, now the next thing that we need to do is we need to actually make connections between the potentiostat and the electrochemical cell. Okay, so we have 3 connectors here. One's up here at the top, and then 2 are down here. And we can track those back to the electrode connections here on the potentiostat. Now the CE, which is the red cable, CE stands for counter electrode. So I'm going to attach that in here to the platinum rod. Okay, so you can see it attached to the platinum rod there. Now, the black cable comes back to the K1 electrode, which is the working electrode. So the working electrode, of course, is going to be the carbon fiber, or rather the carbon disc electrode here. So I've actually brought my alligator clip in and hooked into that. And then the final electrode here is the silver chloride reference electrode. So I'm going to come in and make my connection there to this final alligator clip here, and I'll show you momentarily what the whole thing looks like. Okay, so there's the whole electrode assembly all hooked up. Now the final thing that I want to make sure of here is to make sure that nothing is shorted. I want to make sure that I don't have any wires hitting other wires, okay? Because a short could be devastating to the experiment. All right, so it doesn't look like I have any shorts here. Everything seems to be properly connected. All right, we are indeed on the external mode, and we have everything set up over here exactly as we should. Again, 3 segments. Our first segment is initially starting at 0 volts. We'll scan out to positive 0.8 volts, which should cause oxidation to occur if we have acetaminophen in the solution. Second segment is from 0.8 volts back to minus 0.3 volts. That should cause reduction, the opposite process to occur as we scan back in the negative direction. And then finally back to our original potential of 0 volts in our third segment. All right, so let's go ahead and take a background voltammogram and see how we've done. So I'm going to hit the perform button here, and we'll stand back a little so we can see the voltammogram develop. Okay, the experiment is in progress, and we can actually see current starting to flow here. Okay, so we're moving in an oxidative direction, now back in the reductive direction. And again, this is our buffer solution, so there's no acetaminophen in here, so we shouldn't see a whole lot of current flowing, and indeed we don't. So what we get here is actually a very nice textbook background voltammogram. So again, the voltammogram, if you'll notice, is going to be a plot of the current flowing at the working electrode as a function of the potential that we apply to that working electrode. All right, so again, we notice that there's very little current flowing, and that's exactly what we would expect. So we've actually chosen a good potential window here to look at the oxidation and reduction of acetaminophen. So at this point, you could save this if you like. You could photograph it. At this point in the game, we've had a look at it, so I'm satisfied. All right, so at this point, I'm going to come back to the cell again. And now what I'm going to do is I'm going to take the cell apart and replace the buffer solution that I have there. Let's see if I can get my tripod right. Replace the buffer solution that I have there with a solution that actually contains some acetaminophen. All right, so I actually have a solution of acetaminophen that I generated from the stock solution that was in the lab. And this would be the same solution that you would be using to make up your standards. All right, so I'm going to now unhook all of the connections from the electrochemical cell. I'm going to now pull out the electrode assembly and set it aside. And I'm going to pour out the buffer solution. So I'm going to pour that right back into the waste container here. And now I'm going to come back and take the contents of the volumetric flask, which contains the standard acetaminophen solution, and pour that into the cell container. And you can use as much of it as you wish. So you can see if I've used all of it, I have my cell container about 3/4 of the way full. So I'll place the cell container back in the clamp, and I can shake off the electrode assembly if I like. And I'm going to place the electrode assembly back in the cell container. Okay, now at this point, I'm going to remake my connections. Again, the red is the counter electrode, so it goes to the platinum wire. The black is the working electrode, so it's going to come into the carbon disc. And then finally, we're going to make our reference connection here to the reference electrode. All right, so now the acetaminophen solution is ready to examine. So we are now going to come back across here. Now at this point, I don't really think I need to make any adjustments. We'll run a voltammogram and see how we do. So to come back to run a new voltammogram, I'm just going to come back to the CV parameters, and this is going to restore the very same parameters that I had before. So we're going to take a voltammogram and take a look and see how our current range is doing. As I said, if it turns out that we actually overrange the current, we can come back and account for that. All right, so I'm going to hit perform here, and let's see what the voltammogram looks like this time with some acetaminophen present in the solution. Now notice at this point, current is flowing. Lots of current is flowing. Now the current's coming back down again. And we're getting reduction occurring. And now we're going to sweep our third segment back. Now, here's the problem. You can tell by looking at this voltammogram that we don't have enough current range on our amplifier here. In other words, we're cutting off the current in both directions. So the way I'm going to compensate for this is I'm going to come back to the CV parameters here, and I'm going to go back to the K1 range here, and I'm going to make it bigger. So I'm cutting off at plus or minus 5 microamps, so I want to increase that window. So let's be good and careful and take that out to 25 microamps. And let's see what happens when I run the experiment at this point. So we'll go back to perform with that new current range and see how we did. So now we've expanded our current range, so we should be able to see the whole peak. Aha, there it is. Oh, I'm still cutting off a little bit. So again, you can see there's some trial and error associated with this. Looks like we got the reductive peak this time though, but we still need to back the current off a little bit more, the current range, make it a little bigger to catch the oxidative peak. So again, I'm going to come back to my parameters, and I'm going to say, all right, if I didn't catch it in 25 microamps of range, maybe I can catch it in 50 microamps of range. So I'm going to double that current range out again. I will perform. See how we do this time. I think the solution was a little more concentrated than I thought it was. Ah, looks like we got it that time. Because the concentration is so high, we're getting a little bit of a double peak there, but that's okay. What we want to be able to do for quantitative purposes is find the largest peak for the oxidation process. So again, to summarize what we're seeing here, we're starting here at 0, I'm scanning positively, and now this large increase of current as we go positive corresponds to the oxidation of the acetaminophen. Then I'm going to reverse the scan, I'm going to go negatively, and now this peak back here corresponds to the reduction of the oxidized species that I generated in the first part of the scan at the electrode surface. Now, the next thing you're going to want to do is to quantitatively obtain a current for that peak. So what we're going to do is we're going to left click on the voltammogram, and then I'm going to come back with a right click. And what I want to do is add a tool here. And I want to add a peak height tool, so let's click on that. Now what we're going to see is that we have 2 pink dots, 2 black dots, and a green dot. Now the green dot corresponds to the peak that we want. So what I'm going to do is I'm going to grab the green dot and I'm going to drag it up to the peak of the voltammogram and leave it there. So now what ends up happening is we have the 2 pink dots inside of the 2 black dots. I want to use the pink dots to generate a background here. Okay, so this is going to be a reference point that we're going to use so that we can essentially subtract off any background current that we see. And then the primary thing is to make sure that the black dots lie outside of the pink dots. So now what we have is a current all the way to the top of the peak that corresponds to 39.7117 microamps. And that's the current you would want to write down because we're going to use it to generate the standard curve for that concentration. So again, your voltammogram is probably going to look a little different. At a lower concentration, you probably won't see this secondary oxidation peak here. But this gives you a basic idea of how you're going to generate the data to get the standard curve. All right, so from here, you're going to end up running voltammograms for each one of your standards, and then follow that up with a voltammogram for the diluted elixir mixture. And you're going to generate peak currents for each one of those measurements. And then from that, you're going to be able to generate a standard curve and then use that curve to determine the concentration of the acetaminophen in the children's pain relief elixir.